Okay, guys, this is the first little bit of your semester review for Calc. There's 40 questions. Day one, I'm going to try to get through like maybe 12-ish. Let's do to 13. Okay, that's kind of a good stopping point. So if we can get that many done, that'll keep us on track for the end, I guess. Limits is the front half of this, or front part of this, and it's been like a hot second since we've done limits. So I'm going to do like a little checklist. I think I wrote this up on the board when we did limits before, but like, what do you do first? Like, what are strategies for finding the limits? So number one, first strategy, finding limits. If you want to put this off to the side over here, we have some room, but here are strategies. Step number one, plug it in if you can plug it in. Okay, remember that a limit is like what the y-coordinate should be when the y-coordinate a lot of times like fails. So like wherever you have a hole or wherever you have a vertical asymptote, a lot of times we try to find the limit of like what that value would be if it was there, okay? So the first thing is we try to plug it in. So like number one, I'm finding the limit as x goes to 2, and I'm going to first just try to plug in 2, okay? That would be the square root of 2 times 2 squared plus 1. 2 squared is 4, 4 times 2 is 8, 8 plus 1 is 9, so this is the square root of 9, which is 3. It is not plus and minus 3 because the square root was already there. So basically what this is saying is that at a value of 2, the y-coordinate is 3. Okay, that's what the limit is saying, okay? And there's not even a hole there. There's not even a hole at 3. You know, it actually does have a value at 3. So that's how that one works out. Number 2 is kind of a little bit of a different strategy. So let's talk about number 2. Graphs of 1 over x and 1 over x squared, okay? The graph of 1 over x looks like this boomerangy thing, okay? He has a vertical asymptote at 0 and a horizontal asymptote at 0. Okay, unless he's moved around. And we'll talk about that with this number 2 here. But the graph of 1 over x squared is a volcano. So he looks like this, and he looks like this. So his vertical asymptote is here, and his horizontal asymptote's there, okay? So still at 0, 0, but he is a volcano instead. So that is like the graph. So number 2 is the graph of, this is, his parent function is 1 over x squared. But he is moved 2 units to the right. So what he will look like is 2 units to the right, 1, 2. That means his vertical asymptote is here and his horizontal asymptote is here. And since his parent is 1 over x squared, he is a volcano. So what we're doing is we're saying what is the limit as this thing goes to 2. Okay, so going to 2 is not saying from the left side or from the right side, it's both sides together. So 2 on the right side, I'm coming in and I'm going this way, 2 on the left side, 2 on the right side, I'm coming this way. So on both sides of 2, he's going toward infinity. So he is approaching infinity as you get closer to 2 on either side. If those were going 2 different directions, like let's say I was saying, as he approaches this guy on the left and right side, if he's 1 over x, here he's going to infinity, here he's going to negative infinity. So that would be a does not exist scenario. But since he's going the same direction for a volcano, we would say infinity for that one, okay? All right, I'm going kind of fast. If you need to pause, go for it, okay? That was number 2. Number 3, I try to plug in always, but if I plug in 0, I'm going to end up with 0 on the bottom, so that's not going to work. If I would have, on number 2, tried to plug in 2 minus 2 is 0, that wouldn't have worked either, okay? So always try to plug in first. But number 3 is going to be a scenario when you try to rationalize. So number 3, rationalize. And I'm going to say rationalize square roots, okay? So in this case, that means an E on the end of it. In this case, the square root is in the top. Usually we try to rationalize with the bottom, like when you're doing like i's and square roots and stuff in the bottom. But here we're going to try to get rid of the square root in the top to help us like simplify this. So I'm going to multiply by the square root of x plus 1. Actually, this should be a 9 right here. Can I switch that to a 9? That's a typo. Yeah, I remember that being a thing. I should have fixed that. Sorry. That should be x squared plus 9, or x plus 9. So I'm going to multiply by x plus 9 plus 3. I just changed the sign of this guy. And if I do it to the top, I've got to do it to the bottom. X plus 9 plus 3. Sorry about that typo. I should have fixed that. So that's how that works out, okay? So if we multiply on the top, the square root of this guy plus or times the square root of that guy just leaves us with x plus 9, like it falls out of the square root. Then if I multiply this guy by the 3, I have 3 square roots of x plus 9. Then if I multiply my inside pieces, I have minus 3 square roots of x plus 9. And then if I take negative 3 times positive 3, I get minus 9. Okay, so that's all my stuff on the top. And what you will see is that this guy's going to cancel here, but then the 9s also cancel, right? So all I have left on the top is just x, okay? The really nice thing on the bottom, don't multiply him through. If you remember me saying that when we actually did this section, I'm going to leave him like that because then these x's will cancel. So now I'm finding the limit. There's nothing left on the top. Now I'm doing 1 on the top, square root of x plus 9 plus 3 on the bottom. And now I have to plug 0 in. But I can plug 0 in. So if I plug 0 in, I get 1 over the square root of 9 is 3 plus 3, which is 6. So 1/6 is his limit. Okay, so that's another strategy, is to rationalize if you ever have a square root type thing. Okay, there is that. All right, again, if you need to pause, go for it. We are doing number 4. If I try to plug negative 9 in here, I will get 0 on the bottom, so that's bad. This one is going to be a scenario when I'm trying to factor. So strategy number 4, we're going to factor this guy down and break him down because he's a polynomial. Like on the top, he's a simple trinomial. I'm going to try to factor him and see if something cancels out. What's up?
Yeah, CCC paper for Libby.
Oh, yeah. Where did I put them all? Blah, 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 blah. Hold on just a second. No, I had them back here. Where did I put them? I put them in a drawer. No. Right here. You go make a copy of that. Make 2 and then bring me back the copies. Okay, so we're going to factor this down. This guy's a simple trinomial on the top. Multiply to get negative 27, add to get 6. That would be like 9 and 3. And if we want it to be positive 6, it's got to be x plus 9 and x minus 3. On the bottom is x plus 9. Oh, look at that. He cancels. So now all I have left with is x minus 3. Now, you don't need to know that for this question, but it's just kind of nice to know that because he canceled out, that means there was a hole at negative 9, right? If we set him equal to 0, he's negative 9. He's a hole because he canceled out, okay? So a lot of times the bottom tells me that there's a va, but a va sometimes is a hole actually in disguise, okay? So we canceled out the top and bottom, so now I'm just evaluating the limit as x goes to negative 9 of x minus 3, and now I can plug negative 9 in. And if I do that, I get negative 12, so that's my limit, okay? So if you ever want to cancel that out, when you're factoring, like you're basically canceling out the hole, okay? Or getting rid of the hole in there so you can identify. All right, number 5, it says they want us, here's f, this is this function, g is this function. They want us to find f composed of g of x and find where it is not continuous, okay? So that means I'm plugging g into f. So this guy is going into here, and I want to find where he is not continuous. So if I plug that in, I have 5 over x minus 1, but x to the 4th is going here, okay? And discontinuities occur at holes, vas, and piecewise like jumps. Okay? Or I guess discontinuous could be like the square root of a negative as well. Holes and vas are going to be like dividing by 0. Okay, so we talk about like domain errors is dividing by 0 and a negative inside of a square root. That kind of correlates with discontinuities, okay? But we also have to take into consideration piecewise functions. So this one we have to pay particularly close attention to the bottom. We don't want this to be 0. I don't want the bottom part to be 0. So I'm just going to solve for that and tell what x can't be. X to the 4th, if I add the 1 over, can't be 1, and I take the 4th root. and the fourth root of 1 says, what do you take times itself 4 times to get 1? That would be positive and negative 1. So values for which it is discontinuous, it's discontinuous at 1 and negative 1. So maybe I'll write it that way. Discontinuous at 1 and negative 1. Okay, that's where he is not. That's where he is failing, okay? By the way, as we go through some of these problems, if you are like, wait a second, that did not make sense, put a star by it, and I can talk about it tomorrow, and we can go over any questions that you have, okay? Because I want to make sure that you're understanding this as we go through this. So just so you know, all right? Number 6 is another limit, and they are saying this guy is minus. So that means from the left. From the left. Okay, I got to figure out what we're going to put in strategies. I'm going to say 5 one-sided limits for piecewise. Okay, and the strategy for that, for looking at one-sided limits, is only one equation. You're only going to look at one equation. When you're doing a piecewise, when you're doing a one-sided limit. One side means like here's to the left side, so from the left. Okay, we're looking at coming from the left side, so we just need to look at one of these equations. One of these two equations is going to be from the left, and this determines which one it is. So if I'm talking about from the left, is that x's that are less than or equal to 1, or is it x's that are greater than 1? If I'm coming from the left side, from the left means x's that are less than or equal to 1. So I'm going to look at this function, and what I'm going to do is I'm just going to plug 1 into there. Okay, 1 squared plus 4 is 5, and that will be my limit on that side, okay, on the left side. Okay, now I'm going to do a little hint because I know we have to do it. I think I'm going to ask you this question on number 9. So I'm going to go ahead and do the right-sided limit. You don't have to write this down if you don't want to, but if we were to do the limit as x approaches 1 from the plus side, that would be like plugging it in here, okay? So I would do 2 times 1 plus 2, and that would be a limit of 4. Okay, now, given that information, if I then say what's the limit as x goes to just 1, not plus, not minus, we would look at the left side, we would look at the right side, and we say, those are going to two different things, right? Like one side is coming in and it's touching 4 here, and one side is touching 5 here. I have no idea if that's what it looks like. But we have a jump here, which means that it is not approaching the same number, so the limit does not exist, if that makes any sense, okay? Again, this problem was only looking at the left side, so this is all you had to do. But later on, we're going to be doing both sides together, and so we have to look at each function, what it's going toward, and figure out whether the limit exists or if it doesn't exist. Now, if this was 5 and this was also 5, then my limit would be 5 because they would be converging to the same number. But if it's not, if they don't agree with each other, if they can't make up their mind, the limit does not exist. Okay, all right, so hopefully that made sense. All right, number 7, find the values where this function is discontinuous. Okay, so again, that's like where are their holes, where are their vas, where are their, this type of thing. So I'm going to put a little arrow to that so I don't have to write that down again. Holes, vas, piecewise functions. Now, it says which of these discontinuities is removable? It is removable, or considered to be removable, if it cancels out. So basically, they're asking for where is the hole at? When they say where it's removable, they're saying, like, what value does it cancel out at, okay? Some of them won't be able to cancel. Some of them will. So number 7 says, where is he discontinuous? I'm going to look for the bottom, and I'm going to set x squared minus 4 equal to 0, or not equal to 0. It doesn't really matter. If I add the 4 over, I get x squared equals 4, and I take the square root. So x equals 2. Actually, I'm going to back up. Can I back up? I'm going to factor this down rather than setting him equal to 0. I'm going to break him down. He is a difference of squares, by the way. Difference of squares. I'm going to do x plus 2x minus 2. Okay, you're going to get the same answer, but whatever, it's fine. So I see that x equals negative 2 and x equals positive 2 if I set this equal to 0 and this equal to 0. So he is discontinuous at 2 and negative 2. Okay, now I have to figure out where he's removable. He is removable at the one that cancels. If I look at x minus 2 and then this x plus 2x minus 2, he is going to cancel right here at x minus 2, which means 2 is removable. Does that make sense? X minus 2 is the one that canceled, so I can remove him out, and basically that means I can still evaluate the limit at that point, okay? There is going to be a VA here, which means if I try to evaluate the limit, he is going to be either infinity or negative infinity, right? Like he's going to go this direction or this direction, right? But at this place right here, he had a hole which I can remove out, and then I'm going to actually be able to calculate the limit, okay? So I hope that made sense. If that didn't, put like a star by it or something, and I can go through that again tomorrow. But there is that information, okay? So he's removable at 2. He has 2 discontinuities, okay? All right, this one, number 8. Oh, did I have a strategy for that? That wasn't really finding a limit. That was just discontinuities. Okay, so let's go to number 8. 8 is another limit again, and this is a one-sided limit, but this guy is of the form 1 over x, right? Like that's his parent function. So what I'm going to do is that applies to number 2 again. Does somebody want to tell me that my word graphs is not right? Graphs of functions, whatever. I'm sick. Go with it, okay? Graphs of those functions. So I'm going to refer to number 2, and I'm going to actually look at the graph of this thing, okay? The 3 is only going to vertically stretch a function. We'll talk about him here in a second. But the plus 4 is going to move him to the left 4, okay? So I have the graph of this, and he's going to be going to the left 4. So my va is going to be here, and my ha is going to be here. So the function will look like this guy, and the fact that he's vertically stretched means he's taller. So he's going to be more of a C and less of an L. But that's not going to change my limit, okay? So I don't really even worry about the 3 because that doesn't change. That only changes like the curvature of him, okay? So the deal here is we want to know what was happening to him as he approaches negative 4, which is right here on the left side, okay? So we know there's a VA at negative 4, right? VA at negative 4. So I have to figure out whether he's doing this or whether he's doing this. I can tell from this graph that he's going this way because that's just what a boomerang function does. If this was negative, he would go the other direction. He would go like this, okay? But he's not. So the boomerang is going to go this direction, so I'm going to guess he's going toward negative infinity. But if I want to check, I'm going to pick a number that's on the left side of negative 4, like negative 5, and I'm going to plug it in. So if I pick negative 5, this would be like 3 over negative 5 plus 4, which is 3 over negative 1. So he is down at negative 3, which means because he's negative, he's going downhill and he's approaching negative infinity. That was a lot of information. So what's the answer? Find the limit as x goes to negative 4. He is going toward negative infinity is the answer. Okay, that's what his limit is. And again, that goes back to what the 1 over x value does. Okay, now, if I were to ask you just negative 4 without having the plus and minus on it, I'm talking about like negative 4 on the left side, negative 4 on the right side, right? What would the answer be to that one? If I'm looking at negative 4 both sides together, they're going opposite directions. So that would be does not exist because they're going 2 separate directions. If I was doing the limit as x goes to negative 4 on the plus side, he's going toward infinity, okay? On the left side, he's going toward negative infinity, which means negative 4 both sides together does not exist, okay? So this information you didn't need, but the only answer that you needed to do was negative infinity. But just to clear up some of that information, that's how that works, okay? That was number 8. All right, let's get to going a little faster. Number 9, as x approaches 3, 3 is where my function hops, okay? Now, this goes back to like what I did up here. We're not looking at 3 on the left or 3 on the right. We're looking at 3 both sides together. So what I have to do is I have to look at 3 from the left, look at 3 from the right, and see if those are the same number, okay? If they are, great. If they're not, it does not exist, okay? So let's see what's happening here. I'm going to do the limit as x goes to 3 from the left, the limit as x goes to 3 from the right, and then the limit as x goes to just 3 based upon these two answers, okay? 3 from the left would be less than 3. So I'm going to plug 3 in here, and 3 from the left is going to give me a limit of 9. Let me write that in a different color, 9. If I go 3 from the plus side, that's greater than 3, so I plug 3 in here. That is going to be 10. Uh-oh. Those are not the same number. They cannot agree on the same number, so this is going to be a does not exist. Again, if they were both the same number, then my limit would be, so if like this was 9 also, then my limit would be 9, right? But does not exist because those can't agree. So this was the answer that I have to, that I need. Let me, oh, it's going to move my 3. I'll just erase him. I'm moving him over because otherwise you can't see. I just needed 3 on both sides, but that means I have to look at the left and look at the right, okay? So final answer does not exist because left and right can't agree, okay? All right, these next 2 are going to have to do with as x goes toward infinity. So what's happening is toward infinity means like what's happening all the way over here, forever to the right. This one's going toward negative infinity. It means what's happening all the way over here, forever to the left. And what that's going to have to do with is the horizontal asymptote. So as you're going toward infinity and not a number, all these other ones were limit as it goes to a number, limit as it goes to a number, limit as it goes to a number. Infinities are going to be like forever on the right side, forever on the left side. And the only interesting thing that's going to happen is when he approaches a horizontal asymptote. So like if he's doing one of these, he's approaching a horizontal asymptote. Or he's doing one of these, he's approaching a horizontal asymptote. So basically we're looking for the Haas, okay? The rule for Haas, trig kids, you're going to be like real well versed in this. Number 1, number 2, number 3. You look for n and m. N is the degree of the numerator. M is the degree of the denominator. So if n is less than m, if n is greater than m, and n is equal to m, you have different rules. Okay? So if n is less than m, meaning the top is smaller and the bottom is bigger, he's like going to just sit. He's bottom heavy, right? He's bottom heavy, which means he's going to sit, and his ha is going to be y equals 0, or the limit is going to be equal to 0. If he's top heavy, which means this is bigger than this one, this is small, he is not going to have a limit because he's going to fall over. Top heavy means he falls over, like he's doing one of these, and he's tipping over. Okay, he's top heavy. Top heavy, he falls over, so there's no limit, or the limit does not exist. Does not exist. Okay, that's that. There's no ha, so there's no limit. Okay, this one, if n is equal to m, your limit is the leading coefficient over the leading coefficient, right? So like this first one here, number 10. Your n here is 2, your m here is 2, so your limit is going to be 2/3. That's all. Okay, that one was really easy. These are both really easy. Now, it doesn't matter that you're going toward negative infinity versus positive infinity. Your horizontal asymptote goes all the way through, so it doesn't matter if you're doing negative or positive infinity. It's just saying find the ha. Okay, this one is bottom heavy because it's 1 on the top, 2 on the bottom. And if he's bottom heavy, he's just going to sit, right? He just sits there at 0, so the limit is going to be 0. That followed rule number 1. The limit is 0. Okay? All right, again, pause if you need to, but there is limits toward infinity. Let's do these next 2 and then we'll stop, okay? This one is going back to logs, so we're out of limits. Yay! We're going to logs now. Boo. All right, here's log, here is a log, here's a log. I have 3 pieces and they want me to write it as a single log, put together stuff. Okay, I know plus means multiply and minus means divide, but before I do that, these numbers right here have to go to the back. So this will actually become x squared. The 1/2 power means the square root of y. And this 3 becomes z to the 3rd power. Okay, so I'm going to rewrite that just so it's a little bit cleaner. You don't have to rewrite it. That's log x squared plus log of the square root of y, because these to the 1/2 power, minus log of z to the 3rd power. And then I just want to condense them into 1 log. So I've got 1 log, and I've got a bunch of junk in here. Okay, these 2 are being multiplied. This guy is being divided. So I have x squared, square root of y, over z cubed. And that's 1 log. Okay, so hopefully that made sense. That was condensing. Now we're going to be expanding. And this is an ln, so we're just going to use ln instead of log. Whatever, it doesn't matter. Okay, here we are expanding. All right, so we've got to look at our individual pieces. This is a piece, this is a piece, and this is a piece. Okay, so these 2 are being multiplied and the bottom one's being divided. So let me do my first expansion. I'm going to have ln of something plus ln of something minus ln of something because the bottom one is being divided. So I'm going to do this one first. X squared goes here, x minus 1 goes here, and x minus 2 cubed goes here, okay? The last thing is this guy has an exponent, so I'm going to move him down in front. So he's going to have a 2 there. This guy doesn't have an exponent, but this one does. He's going to go down in front, okay? And so the 3 is going to go there. So this is 2 ln x squared. No, the squared's not there. 2 ln x, you can leave the parentheses or you don't have to have them. Plus ln, this one has to have parentheses, x minus 1, and then minus 3 ln of x minus 2, okay? And that is expanded all the way. There's nothing more that you can do, okay? All right, I'm going to stop there. That's 13. That's good to go. I make sure you put a star by anything that you had questions on, and I will go over those tomorrow. If you want to start doing some of these below, that would not be a bad idea, and then just check your answers so you're kind of like studying at the same time. That would not be bad, but I can answer any questions that you have tomorrow, and that's it.